Hey everyone, my name is Pry, and today we'll be talking about a paper that I like, which is chain replication, presented, of course, by Renice and Schneider at OSDI 2004. Here's the paper, and once again, 2004, meaning that it's roughly 20 years old now, which is pretty wild. But this is what the paper looks like: chain replication for supporting high throughput and availability. I'll leave in a link for it in the description below. But let's get into it. So, to motivate the problem that they're solving, they want to build a performant and fault-tolerant storage system and build sort of an architecture for that in a distributed system context. So we'll describe what performant and fault-tolerant mean, but first let's talk about what a storage system is. So a storage system should support read operations and should support write operations. And in general, I think it's best to think about this as sort of like a hash table. Essentially, you can read a key and get a value associated with it, or you can write to a key and give it a value, that sort of thing. But really, it doesn't matter. It can be any data structure. It can be anything that has read operations and write operations, updates and queries, so on. And for performance, we mean latency or throughput. So latency is kind of the amount of time that a single request takes to complete, and throughput is, hey, how many requests can I do per second? Throughput is really about multiple requests. And fault tolerance is, hey, can we actually deal with some sort of like hardware failures or network failures? And so clearly, like a fault tolerant system can't just be one machine, because one machine, say it accidentally, like the power gets unplugged, or unfortunately just the hard disk dies or something. That's a failure that a single machine can't recover from, but a cluster or a distributed system can. So additionally, the paper has a failure model, and they consider what's called fail stop, meaning that they just kind of assume, hey, we've got a bunch of machines and any of them can kind of just fail and stop working and they're not going to ever return. This is a pretty simple failure model, but of course, chain replication can be extended to deal with more complex ones like fail recovery. So here's sort of the main idea of chain replication. Each of these nodes, sort of shown here, are arranged in a linked list sort of formation where we've got a head, we've got a tail, and we've got some inner nodes. For now, I'm just drawing 3 because it's sort of easiest to show. And there's a configuration manager, which we'll sort of peel back later and show who's really sort of behind the scenes. And writes and reads are handled differently. So let's look at the context for writes first. First, we've got a client, and say a client is wanting to write some key to some value. Well, the write goes directly to the head first. And once the head receives it, the head sends that write message over to the next member of the chain, and so on, until it reaches the tail, and then the tail sends an acknowledgement back to the client saying, hey, I received your write, it's been committed. So kind of the idea is that each node in the chain is actually a complete replica, and they're all moving in lockstep. And once a write finally reaches the tail, that write is committed. And so we send that acknowledgement. For reads, it's a little simpler. The client just sends a read to the tail, and the tail sort of looks up in its in-memory or in sort of, I guess, disk or whatever sort of storage. It's got its own data structure. It does the read, and it says, hey, all right, I'll give you the value. And the tail handles every single read. And it's all just processed at the tail. And what about this configuration manager business? The configuration manager is what's storing sort of the whole like idea of the chain, and it's actually the one that's detecting failures. And so what sort of software is this? Well, it's something like Apache Zookeeper, just the best, right? What a cool guy. And essentially, any other sort of Zookeeper-like cluster management software would work, something like Console or etc.d, don't really know how to say it. Yeah, so there's those. And let's sort of maybe discuss what that looks like, really. So the configuration manager, the paper says, hey, quote, we assume that the master is a single process that never fails. They call the configuration manager the master, all right? And this is clearly sort of unrealistic on a single machine, right? Because, hey, machines can fail. But the paper and pretty much everyone in the real world relies on some sort of cluster management software on many machines, something like Zookeeper or etc.d and so on. And these use a consensus algorithm, something like Paxos or Raft. Consensus is unfortunately sort of out of the scope of this video, but essentially all we sort of I need to tell you about is that in terms of failures, Paxos or Raft or consensus in general requires a majority of nodes to be up. So in this example of 5 nodes here, 3 of them need to be up for the cluster management software to keep running. And it has the strongest sort of consistency model of any distributed system, which is linearizability. And so essentially, yes, you have 5 nodes here in the best case, but really they're acting like one machine. And you can really think about it as one machine as you're programming against it, which is nice. But okay, let's move on with chain replication. How do you actually deal with failure of a chain? What happens if we break the sort of metaphorical chain? Well, we've got 3 different types of failures. We've got head failures, we've got tail failures, and we have internode failures. And each of these have to be handled in a distinct manner because the head and tail are special. So when we deal with a head failure, we essentially need a new head. And because the head has failed and clients are sending write requests to the head, unfortunately, the clients are not actually receiving ACKs. They're not actually getting their writes through. So writes are temporarily unavailable when the head is down. So how do we detect this? Well, the cluster management software, whatever it is, detects that there's a failure and says, and typically this is through something like heartbeats, which is essentially every single node here is constantly, every so often, sending a "Hey, I'm alive" message to the configuration manager. And oh no, looks like the head has stopped sending these heartbeats, and we have to assume that it's dead, even if maybe the network just went down or something, right? But anyhow, the cluster management software detects it and sends a new configuration to the rest of the nodes saying, "Hey, linked list has got to change, guys, and you, node number 2, are now the head." And we get rid of that sort of link, and now writes can be accepted again. With the tail failure, same thing, or similar thing. The tail failure is detected. The predecessor node is told, "Hey, you're the new tail." And important thing to note, because of the tail's sort of importance in chain replication, writes are not able to be completed, and reads aren't able to be completed. So actually, the tail failure is kind of worse, just because it really takes down a lot of the capabilities of chain replication. Importantly, though, writes can still be accepted because the head is still alive and the client is still able to keep doing it. It's just that those writes can't complete until the failure recovery process is ended. And we've got this new tail. And finally, let's look at what happens with an internode failure, which is pretty complicated. And there's a lot of sort of extra bookkeeping. So let's go through it. First of all, the cluster management software once again detects, hey, an internode has failed. And I've labeled these nodes P and S for predecessor and successor. And essentially, there's a problem, which is that writes might be lost in the middle. So each node actually has to keep track of a set of in-flight writes, which we'll describe later. And so essentially, it's detected. We first send the next configuration to the predecessor. And the predecessor is like, oh, okay, now I know my new successor, not this node, but this node. And then it actually sends its in-flight writes to the successor. Because who knows, this node might have failed before it actually sent over those writes. And then the cluster management software finally sort of says to the successor, hey, you've got a new predecessor, and the chain is complete again. So let's talk about the in-flight writes. Why do we keep track of them? So let's look at this once again. Simple chain example. We've got a head here, we've got a tail here, we've got a client here. So client wants to do a write, it reaches the head sends it over to the next node gets it, and right before the next node is able to send it off to the tail node, unfortunately it dies. And this write is not fully finished. Let's imagine a failure recovery mode where we don't have in-flight sets or sort of in-flight tracking. Well, we get rid of that node. Let's move that node over. And now our chain is complete. But oh no, look, our chains, our replicas, are these two nodes don't actually have the same contents anymore. And sort of a key invariant of ours has been broken, which is that all the replicas should be the same. Once sort of like we do all this write propagation. So our replicas have diverged, and there's no good way of sort of dealing with this that I can think of immediately, except for this in-flight tracking scheme, which is very simple, which is why I think it's beautiful. So when you receive a write request, every node actually keeps track of this set of writes that it's not seen completed yet. And each node gets that until the tail, and the tail doesn't actually keep track of these because it's the tail. Any write that gets to the tail is automatically done, so to say. So we do the ACK, and then the tail also sends an ACK back through the chain. Once this inner node gets that ACK, deletes that from the set, sends another ACK back through the chain, and so on. And so this is how we keep track of these in-flight sets, and this is how we remove them. So finally, let's talk about some metrics for describing or sort of measuring how good chain replication is compared to other things like consensus. So for consistency, and consistency is really, as a programmer, if I'm doing reads and writes, what's the sort of behavior that I can expect from a distributed system? And chain replication scores really well. It's linearizable. It is the gold standard for consistency. You can really think of it as a single machine, even though it's a distributed system. So this is really good. And I think it's only fair to really sort of compare this to other linearizable distributed systems. Let's look at availability. How many failures can it tolerate until it becomes unavailable? Well, if there's n nodes, it can tolerate n-1 failures. As long as a single node is alive, that node can act as the head and the tail, and it's still good. So this is very high availability, I would say. Of course, this is sort of cheating almost in a way because it's depending on something like Zookeeper. It's depending on a consensus algorithm. But for now, we're sort of just looking at just chain replication. But of course, it's only as available as its cluster management software is. And that's the sort of a common pattern. Finally, or not finally, we'll look at latency next, which is, once again, how long a single request takes to complete. And this is where chain replication has a downside, a con, which is that because of the many network hops that it takes, you have to go through this whole chain. Unfortunately, the latency can be pretty high relative to even something like consensus. So that's something to consider. But they designed this for throughput, and the throughput is really, really high, I would say, compared to other linearizable protocols. So if you need high throughput, if you need to deal with a bunch of writes, this is really sort of a good architecture. And we can sort of also see this latency versus throughput trade-off, where if I want low latency, maybe I don't get high throughput, and vice versa. Maybe if I get high throughput, I might not get the lowest latencies that I want. So yeah, hope this explained chain replication well. What's next? I still want to sort of create these videos on papers that I'm reading. I like reading papers a lot. So I think maybe a next step is to read the crack paper, which is really cool. It's all about how, hey, we can get rid of this limitation of chain replication, which is that all of the reads need to go through the tail. And crack does away with this in a really clever way. And anything that's chain replication in the real world uses this optimization. We can also talk about what is linearizability, what's the formal definition. Consensus, we can talk really about any of these papers. So if you have a suggestion, leave it in the comments. And thank you for watching.